Let's now look at the destructive features of earthquakes. If you go to the PowerPoint, it should be slide number 18. And so many of these are really obvious. Let's go to the first one. And if you actually get the slide or the PowerPoint that I'm showing you, and if you look at it in, if you actually show it as a slideshow, you'll see all of the pictures, and they're all GIFs. So they should you should see what's happening in those pictures. First one is ground shaking. So obviously ground shaking, we're talking about our love waves or our Rayleigh waves, and this is simply the surface of the earth is moving around. Some of these movements can last up to 90 seconds. And we often find the movement is shear movement, it's back and forward, and there is a great deal of displacement. Cool. What happens here? Well, most stuff falls over. Buildings collapse. Cars are moved around. People are crushed. Pipes like sewer pipes, gas pipes rupture and split. Now, this movement is, it's actually very interesting what a lot of people say about this, and there's a bit of research on the reaction of animals to a lot of earthquakes. Some people believe that animals can see things or feel things greater than them, and I think there is some validation to that. I know that animals certainly will have they're on the ground, they can sometimes sense earth movements before we feel them. And if you're thinking about primary waves and secondary waves and love waves, as these waves come in different forms, the faster that some waves come in, so a primary wave will move very, very fast, so there's actually a chance that some animals might actually feel that wave and that might startle them, whereas we might not even notice that wave was occurring. All right, next slide. Let's go to our landslides. So landslides are another form of mass wasting. It's called mass wasting. And it's a massive movement of rock or debris. I guess the biggest danger here is that people will get buried under material, and landslides are often triggered in areas that are already prone to landslides. So on slopes or areas where the ground may slopes or the ground may give way. The ground may Well, the problem is that the earthquake will trigger it. Cool. There's some great little images of some of these on the slide, on the PowerPoint. It's not only landslides though, if you think about it. What also, if we're thinking about mountainous areas, earthquakes can also trigger avalanches. Again, we're talking about a movement that displaces the rock. Cool. All right, let's move on. Get that there for you. All right. So, a tsunami. The word for tsunami is Japanese for harbour wave. They are not a tidal wave. They are not a tidal wave. There's nothing to do with the tides in terms of a tsunami. So a tsunami is a long surface wave of water. It's a surge of water that makes its way onto land. Real emphasis on the word surge. A tidal wave is not the traditional wave that you see, the Japanese diagrams. I can't remember the name of the picture now, but it is not that huge wave. It is more a surge or a push of water up onto the land. Let's just talk about, before we talk about how they're generated, let's just talk about what they look like in water. So they're very interesting because their speed is differs greatly. They are a long amplitude wave. So if we think about long and short amplitude waves, well, if we think about, we've got here, there's our other normal. Think about so this distance is the amplitude, and obviously a tsunami has a very long amplitude. Now, because it has such a long amplitude, it means it behaves a little bit differently from regular waves. It means that it travels at different speeds. Dependent on water depth. The deeper the water, the faster the wave. And there's a little diagram there I show you that I've got on the slide there. That we've got depth of water about 5 kilometres deep. We've actually got a speed of about 750 kilometres an hour. When the depth reduces, we get to about 1 kilometre deep. The speed again reduces to about 280 kilometres an hour. Why? Because it's a longer amplitude, it needs greater depth. once we get down to about 50 meters, it's only moving at about 79 kilometers an hour. So it slows. Doesn't mean it doesn't get any less violent, but it just slows. Ships that have been in the middle of the ocean have not noticed that a tsunami has gone over them because the amplitude of the wave is so low. There is actually such little wave height. The closer a tsunami gets to shore, the greater the water height. All right, so that's the first bit. Let's now look at how a tsunami is formed. There are 4 steps to forming a tsunami. Step number 1. We have faulting or displacement of rock. This is the sea floor. Fault. Now, we've got our fault and we've got our movement this way. What's going to happen? We're going to have uplift. This is moved up and that's moved down. Faulting or displacement of rock that cause uplift of the sea floor. I'm going to write here, faulting or displacement of rock causing uplift. Uplift is really important because it's that drives our tsunami. So this is the sea floor. Good. All right, next one, number 2. Displacement of the water above. So here's our sea floor. Here's our ocean above, and this is an exaggeration. This area here, I could have gone a little bit further down this way perhaps. Ocean displaced. All of this rising lump of land has caused all of that water to bulge upwards. And we have the upward wave, the initial wave formation. Okay, so faulting or displacement of the rock causing uplift. So we've got uplift. Now we've got uplift, we've got displacement. All right, next step. Our next step in our formation is the propagation of the wave outward. Propagation of the wave outward. Okay, so let's say, for example, I'm going to look at a bird's eye view now. Here we have, let's draw a continent. Let's draw a land area up here. For example, I'm going to try and draw some Indonesian islands. Okay. I'll draw another landform here. I don't know, these are just random places. Now, if our earthquake occurs here, then the wave propagates outwards from that central location. Just like ripples in a pond. So the wave propagates outwards in all direction. The last step is what happens when the wave finally hits land. Cool. Okay, so we've got our our 4 steps for the formation of a tsunami. Number 1, initial faulting and displacement. Displacement of water, the propagation of that water outwards, and finally our wave height increasing as we get closer towards land. Still going on about tsunamis. Fortunately for you guys, you're able to look at some actual great footage of tsunamis. If you look up the 2004 Boxing Day and the 2011 the Fukushima and the Boxing Day tsunami. Really terrible, but fascinating footage. So what are the first indications of a tsunami? Because I guess we're looking at hazards, how we deal with them. What is the first thing you notice when a tsunami comes along? And that is drawback. That's where the water retreats outwards. It was said that for the people who witnessed the Boxing Day tsunami, they were drawn out to the seashore because when the wave went out, it took with it all the water, obviously, and exposed lots of shells and fish and lots of things that were really interesting for people to collect on the beach. And of course, people went out there not realizing that a few minutes away was an oncoming tidal surge or tsunami, which was very deadly for a lot of them. So drawback is that first warning. If you see drawback, you're at the beach and there is drawback, first thing you want to do is probably get away as fast as possible. What about other warnings? Well, there are other sort of warning systems for tsunamis, and that is called the DART system. Let's start that again. And the DART stands for Deep Ocean Assessment and Reporting of Tsunamis. I don't know why they didn't call it DOART, or anyway. It's DART. And what it is those loads of little buoys that sit out in the ocean, and they will sit out on the sea floor and they will monitor what's going on below the surface. They're actually quite interesting and quite delicate little things. Below the surface, they're actually anchored to the sea floor. And what happens is when a wave lifts them up or lifts them up a certain amount, it sends a signal that there is a possible tsunami on its way. So the DART measures ocean temperature, water pressure, and wave height. It does this every 15 minutes. And if there is a abnormality or something that's a little bit out of the ordinary, for example, if the water pressure suddenly increases, well, then that means that there's a chance that there is a tsunami. Now, they match that data with any earthquake data. So they use this data in conjunction with other seismic readings, and they use that to send out a warning system to people to let them know that a tsunami is on its way. There are a number of tsunami warning systems. Let's see. There is the. Just trying to think of the tsunami systems we have in the Pacific. There's the Pacific Ocean. There's the Pacific Warning System. So there's the Pacific Tsunami Warning Center. This would actually, this gives out a lot of information. PT WC. There are a bunch of others. The US have a number of them as well, and there's also a few in the Atlantic. So, but the Pacific is the main one that we're interested in. So have a bit of a look at their website. It's actually interesting, some of the stuff that they've got going on there, and they explain all about how DART works and the different types of, warning systems that they have. All right. So let's keep going with impacts of earthquakes, and let's look at liquefaction. Oh dear me. So, have you ever gone to the beach and sank into the sand? Well, if you have, then you've felt liquefaction firsthand. If you think about beach and sand at the beach, there would be lots of sand grains, and they would be all joined together like so. There would be very few spaces between them, and between them there would be a little bit of water. Water comes in and fills in these little holes here. But most of the contact is actually between the sand grains themselves. Sand grains in contact. Well, during liquefaction, these sand grains are spaced apart by water. Water fills into these gaps, separating the sand grains. So this solid that was once a solid sand beach, all of a sudden behaves liquid. So water fills spaces. So sediment will move or flow. So let's write down a definition of liquefaction. Okay, so liquefaction forces water into the grains between sediments. So into the pore spaces between sediments or rock particles or soil particles, and it makes them behave like a liquid. Now you can imagine if you've got a house. No, let's not go with a house. Let's go with a block of flats. I don't know why I'm drawing it like this. Anyway, you've got a block of flats. Let's put all the windows in. Doesn't look very steady as it is, but you can imagine if part of this soil here and land started to behave like a liquid, then what's going to happen? Well, that building is going to topple over. This is actually something that we're possibly in danger of here in WA, since most of our buildings are built on sand and there is water between those. If there was a significant earthquake to occur here, I would expect many of our buildings to suffer the same fate, not only by the shaking of the earthquake, but also by the liquefaction causing the soil to liquefy before them. Another effect of earthquakes is quite an obvious one when you think about it, and that is fire. Fire kills so many people. Why? Because gas lines are cut or break. So the gas is ignited. The trouble is, though, is at the time that this is occurring, so we have an earthquake and it ignites a fire. Well, that's great. What do? You call an ambulance and you call a fire brigade. But you can't call a fire brigade because at the time they can't get there because the roads are blocked. So these occur at the same time as other disasters e.g. buildings collapse, roads are blocked, so emergency services can't get there. That means the fires continue to burn and continue to break. Let's try and draw a little bit of a picture of that. Okay. So we got a house, a building on fire. Sorry, Yasmin, it's not going to be as good as your diagram. What's caused it? By broken gas lines. You get the picture, all right? So we've got a whole series of accidents occurring at the same time. Because they're all occurring at the same time, the emergency services simply can't get out there to save people. Or this might have happened in a time like in 1906 in LA, or 1923 in Tokyo, where people were just, most people died because of their exposure to fire, and they just simply could not get away. I will say one other thing, and I'll write it down the bottom here as well. We've talking about broken gas lines, but it's also important to mention that it's not only gas lines, sewage lines and water pipes. they also leak. So you can imagine what happens when the sewage pipe leaks and that water goes into the water pipe. People go to have a drink, and next thing they know, they get very ill. So another big problem that's linked to fire, and I guess linked to this issue, is disease. That's more of a long-term issue though. Drinking the pooey water. Okay. Just one very quick little quick case study for you to do before I finish up on this. And that's an earthquake in a place called Kobe in Japan. It's a favourite of teachers. It occurred in 1995 and it was a 6.9 Richter scale earthquake. And it was 17 kilometres deep. So it was very shallow. 5,500 people dead. How did people die? Well, 4,800 of them were crushed. They were crushed in their homes. 500 of them, or I should say 550 of them, were burnt to death in the fires. And there were 120 others. Well, these are all approximate numbers, by the way. They died in other ways. This is a very interesting number because you see 1995 wasn't that long ago. Well, it was for you guys, but it wasn't really that long ago. And I remember when this earthquake happened. And a lot of the modern buildings stayed up. So, this earthquake highlighted the need for countries to not only develop earthquake-proof buildings, but to ensure that older dwellings were also safe. So, most of the people that died in Kobe, they died in the old part of the town, down by the I guess what was the old fishing village at the time. And most of the buildings there were fairly small, but they were fairly simple. I guess I'll try and draw to you what they look like. There was something unique about Kobe architecture. Is that their houses were, well, I guess they looked a little bit like this. They had quite thin walls. And I'll just try and then they had these massive roofs. Oh, wrong colour. Oh, let's go with a red. So, it's not great. Let me make this. So the roofs in the houses at Kobe were huge. Big, massive, heavy roofs of their buildings. And what it meant was they were super top heavy. The walls of the houses, the traditional houses there, were thin. Thin walls. Heavy roofs. They also were covered in tiles. Now, what did that mean? Well, what it meant is that during the earthquake, these walls gave way. And people were crushed. That's how a lot of the people died at Kobe, or the foundations of the house simply could not cope with the weight of these massive roofs. So what they had to do after this is they had to introduce something called retrofitting. And that's what I'm going to talk to you about in our next lesson. I suggest you guys do a little bit of research on Kobe and have a look at what happened and I guess why people died. It's something important you should know. All right, thanks guys, see ya.